Yeah, just let me know.
Okay. It's live now, Honor.
Okay, great. Thanks. Okay, I think we can get started. Yeah, as I was mentioning, hopefully we will have the next meeting in person, live streamed from the classroom after we test the setup. But today I'm going to cover another example review of the RowClone paper, which has an exciting idea that has had significant impact. Last week, Mohammed reviewed the Gatekeeper paper as an example review, and he also discussed issues in bioinformatics and genome analysis, accelerating genome analysis in general. And today I'm going to also review the paper and then also discuss some of the topics related to it. That's why I titled as RowClone and processing using DRAM. And this may actually form some of the papers that you may select. Not this particular paper, but some of the papers you may select that actually can get tangentially discussed in this meeting. Okay, so let's get started. Remember, this was the suggested paper discussion format. This is a good, well-tested method of analyzing papers in general. Basically, we want you to give a 20-25-minute summary and 10-minute critique plus 10-minute discussion. So hopefully everything will fit 40 to 50 minutes, let's say. And the first part is really the summary of the paper. And the second part is more discussion of strengths, weaknesses, alternatives, new ideas and problems, and questions. Hopefully a nice discussion in the seminar. So I would like to ask everyone to participate as much as possible in the discussion. So we will probably have around 8 sessions of presentations. We will finalize it, but before that, we will give you a set of papers to select from. We will likely start later in the semester so that you can prepare better. And there'll be presentations in each of the, well, that should be 8, I think, not 11. Yeah, in each of the 8 sessions. And we would like to ask you to have max 50 minutes total for each presentation plus discussion. And we will take the entire 2 hours in each meeting. And each presentation is basically one student presents one paper and leads discussion. As I discussed, I'm going to give you an example of the summary and analysis and critique and discussion. Please follow the suggested guidelines because that way I think you can also improve how you present papers. For many of you, this is going to be the first time probably presenting papers, technical papers, and critiquing them. So having this methodology to critique them is going to be important and hopefully helpful to all of you. Okay, now let me, just to remind you, there's an algorithm for presentation preparation and study our lecture 1B. I don't remember if it's 1A or 1B this time, but for presentation guidelines, read and analyze your paper thoroughly, discuss it with anyone you wish, use any resources you want, and prepare a draft presentation based on the guidelines, meet mentors and get feedback, revise the presentation and delivery, and then meet your mentors again and get further feedback, and then revise the presentation and delivery again. These 2 meetings are extremely important and they're required so that you can actually polish your presentation and get good feedback on it. And you have to schedule them with your assigned mentors. We will assign the mentors after we assign you papers, after you make your choice of papers, of course. And mentors may suggest meeting times, but please reach out to them so that you can schedule meetings. And practice is very important in delivering these presentations. The more you practice, in general, the better, because you learn also how to actually deliver talks as you keep practicing. Okay. Okay, if there are no questions, then I will jump into some example, one more example paper presentation. We'll do some of these as we, until you start presenting papers, basically. And learning by example is a great way of learning, as we discussed at some point. We will do at least one more, well, specifically one more paper today, since I'm going to cover related topics also. Okay, this is the structure of the presentation that's recommended. I'm going to go through it. Basically, background, problem, and goal, and then novelty, key approach and ideas. What does the paper do? What are the mechanisms in some detail? What are the key results of the paper? What is the methodology? What is the evaluation? And what is the takeaway summary? What are the strengths? What are the weaknesses? What are your thoughts and ideas related to the paper? These are more discussion now. And then key takeaways. And then it goes into open discussion, basically. I'm going to basically show you by example all of this structured way of presenting the paper. And let's start then. If no one has questions, I will just get started. I don't see any questions anywhere, so I'm going to get started. So this is the paper. I'm a co-author of this paper. This is one of my PhD students, Vivek Seshadri's work that went into his PhD thesis. The paper is titled RowClone, Fast and Energy Efficient in DRAM Bulk Data Copy and Initialization. And it was published in Micro in 2013. And it's always good to start your presentation with describing what I just described, basically. What is the paper and where it's published and who are the authors who are clear. So I'm going to use a lot of slides that Vivek actually prepared through iterations that we have done to prepare the slides, basically. And the slides have become better through those iterations, clearly. Just like you are going to do with your mentors, that's what I do with my PhD students also. We iterate over the slides so that they become, let's say, extremely good, so that they can have a nice impact on the audience and also convey the topic really well. So this is the paper. This is a collaboration with Intel. At the time, I was at Carnegie Mellon. So let's start with the first part of the presentation. I'm going to give you background, describe the problem and the goal that the paper is targeting. So memory channel is a bottleneck in existing systems. It basically is between the memory controller and main memory. And because it has limited bandwidth and it consumes high energy, these are energy hungry interconnects, essentially. So you don't want to exercise them much. So the goal of this paper is really to reduce the memory bandwidth demand. We want to, the paper targets to reducing unnecessary data movement. And it's going to specifically focus on one issue that causes unnecessary data movement. And remember, data movement is important because DRAM access, data movement from DRAM dominates energy compared to computation. Computation is cheap, as you can see in this picture, as we have also seen in an earlier lecture. But memory access is really expensive in terms of energy as well as latency. Okay, and you can see the relative numbers over here. So this paper targets one source of unnecessary data movement or energy inefficient data movement, which is bulk data copy and initialization. In many cases, in applications and systems, you want to copy data from one place to another place, source to destination, or you want to initialize a destination value, and you want to do it in bulk, meaning that you want to copy 4 kilobyte pages, for example, or 1 megabyte pages, or 1 gigabyte pages. And you want to initialize maybe a whole database, 1 terabyte database. And this clearly consumes a lot of energy and performance. And the goal of the paper is to alleviate the issues caused by this sort of data copy and initialization. And there are past works that have actually targeted this, that have talked about the impact of this data movement on system performance. As you can see, there are some papers that are written. I would actually recommend you to take a look at these papers if you're interested. They're relatively old papers also. And people have tried to add some hardware support for this sort of data movement, but they haven't gone to the extent this paper has gone to. They did not do it inside the memory chips, for example. This paper is going to provide support inside the memory chips for this sort of data movement and initialization. But establish that this data movement and initialization is clearly important for applications and systems. And you can see some example applications and system calls that lead to data copying and initialization, forking, virtual machine cloning, page migration, initialization of pages for security purposes, and as I mentioned, initialization of a whole database, for example, before you start it out. It can take a long time, and it can be energy efficient if you're actually going through the processor for all of this. And recently, after this paper was published, Google published a paper in ISCA 2015 that basically says that these two system calls, memcmove and memcopy, only two system calls, variants of these, consume 5% of all of the execution cycles in Google's data center across all workloads. Now, this is significant because 5% is a very large number if you actually average it across all of the workloads. And these, we're just talking about two system calls that do data movement, as you can see. So we're going to get back to this paper, actually, when I give you the historical perspective of RowClone. You can see that this Google paper was published after RowClone, and they're going to reference RowClone and say that this is a good way of alleviating the impact of these data movement function calls. Okay, so what is the shortcoming of today's systems when you're actually doing data copying? So if you want to copy the source page, white page, to the gray page over here, today you have to go through the processor. You have no other option, basically. You need to bring the data into the processor, into the caches or the memory controller. You need to bring the destination page, and you need to copy the source page to the destination page byte by byte. And then you need to write back the destination page to memory. And this is clearly high latency because you're accessing memory multiple times for 4 kilobyte page. But imagine doing it for 1 megabyte, 1 gigabyte. So as you increase the data size, data copying size, this becomes a bigger bottleneck. And high bandwidth utilization on a very important system resource, which is the memory bus. This could cause cache pollution, but you could eliminate that by doing it only through the direct memory access engine, through the memory controller over here. You don't need to disturb the cache hierarchy, but that assumes some different programming that you need to do. And this causes unwanted data moment because maybe the page you're going to copy data into, you're not going to reuse anytime soon. It may take a long time, actually, until you really need it. So it doesn't make sense to bring it into the caches right away. So this paper shows that for a 4 kilobyte page copy through the direct memory access engine, not even going through the cache hierarchy, by doing it in the memory controller, like other state-of-the-art works have proposed, you consume about 1,000 nanoseconds and 3.6 microjoules, depending on the state-of-the-art technology at the time, basically. And the paper questions this, basically. Should we actually do it by going through the processor? And that's what brings us to the novelty, key approach, and ideas. That's the second part of the structured presentation. So the idea of the paper is to do it inside the memory. Basically, the paper says we should not be disturbing the processor if it makes sense, or when it makes sense. We should just do it on the memory side. And that's the idea, basically, at a high level. You copy the source page to the destination page just inside memory. Nothing else in the system gets disturbed. This is low latency because we're going to use the internal structures inside memory. This is low bandwidth on the memory bus because we're not going to transfer any data. This is going to cause no cache pollution because we're not going to even touch the cache hierarchy. As you can see, we're not going to even touch the bus over here. And this is no unwanted data moment because if the copy data is not going to be used anytime soon, you're not going to transfer it. Basically, you're going to transfer the data only when it's needed to the processor. And the paper shows that you can reduce the 1,000 nanosecond latency to 90 nanoseconds. That's more than an order of magnitude improvement. And this energy, 3.6 microjoules, to almost 2 orders of magnitude lower to 0.04 microjoules. Okay, now let's take a look at the key idea, key approach of the paper. And this is the real key idea of the paper, basically, doing it inside the DRAM subarray. DRAM main memory consists of subarrays. The paper targets DRAM, but the idea was shown to be applicable to other technologies later on, as I will discuss. The paper targets DRAM. So DRAM consists of rows, and you have many rows inside a subarray, and then you have a row buffer, which is essentially a row of sense amplifiers to amplify the data. The paper takes advantage of the row buffer as a temporary storage to move the data or copy the data from a source row into the row buffer, and then from the row buffer into a destination row. That's the idea, basically. It's as simple as that. Basically, how is it done? You activate the source row first, which brings the data into the sense amplifiers, which is the row buffer. Now the data is strong, captured in the row buffer. Now after this, you activate the destination row while at the same time deactivating the source row, which means that once you activate the destination row, it gets connected to the row buffer, and the sense amplifiers with their strong data, they drive the data into the destination row. So basically, row buffer is an intermediate buffer to capture the source row, and then source row gets copied into the destination row. And the key idea is to do 2 consecutive activations. And the hardware cost is negligible for this, as the paper shows. Okay, let's go into mechanisms in some more detail. This is the best mechanism of the paper, if you will. So the paper covers DRAM chip organization. If you look at a DRAM chip, it consists of banks, and it consists of chip I/O and the memory channel, as you can see. And banks share a bus so that they can communicate their data outside of the memory channel, and they can get data from the memory channel and write it into them. Keep that shared bus in mind. So if you look internally into a bank consists of multiple subarrays, let's say 128 subarrays or so. So these subarrays share a bank I/O logic, but they're mostly independent of each other. And if you look at a subarray, each subarray is a 2-dimensional array of DRAM cells, and you have rows and columns, and there's a row buffer in each subarray to sense the data. So what I showed you in the earlier picture to do the 2 consecutive activates, that was at the subarray level. Okay. So basically, RowClone enables data transfer within a subarray, like I discussed, across banks, as well as across subarrays in the same bank. And these are different mechanisms. So what I described to you earlier was what's called fast parallel mode in the paper. This is intra-subarray or within subarray row clone. This is row granularity. Data is copied at a row granularity. And we're going to look at that again, and we're going to talk about the implications. But the paper also introduced a mechanism called interbank row clone, which is at the byte granularity. It calls it pipeline serial mode. Basically, you can transfer byte by byte from one bank to another bank. And the paper takes advantage of that interbank row clone to do also inter-subarray row clone. Now, I should say that later works actually improved these mechanisms, interbank and inter-subarray row clone, significantly. I'm going to briefly mention them. I'm going to talk about them as described in the RowClone paper, but keep in mind that later works that have happened within the course of 8 years after this paper was published greatly improved this one and this one. Not this one, though. The first one, the core idea, is one of the fastest mechanisms to copy data inside DRAM and inside any main memory today. Okay, let's take a look at that core idea again. So basically, you have fast parallel mode. We're going to go into a little bit more detail here. You have the source row and the destination row. Basically, the key idea is to bring the source row into the row buffer with first activate, and then move the data in the row buffer into the destination row with a second activate. So it works nicely. Clearly, we know how to do this first activate, but how does the second activate work? This requires some small change to the DRAM chip or the memory controller, or both. So let's take a look at a little bit more detail. This is the source row. I'm showing only 1 bit. This is the destination row. I'm showing only 1 bit. It could be 4 kilobytes, clearly, as we discussed. I'm going into one level down in the abstraction layer. You can see the bit line. You can see the sense amplifier. I'm basically showing the components that are required for understanding. I'm not showing all the rows in the bank or the peripheral circuitry. I should have said all the boards in the subarray or the peripheral circuitry. It's just one cell here, one cell in the source, one cell in the destination row. These are capacitors because this is DRAM, and one sense amplifier in the bit line they're connected to. Okay, let's assume that the source cell is initially completely charged. Initially, the bit line is pre-charged and nothing is connected to the bit line. And the sense amplifier is also pre-charged, as you can see. Both ends are VDD over 2. So the way sensing is done in DRAM is you activate the source row, which essentially connects the access transistor, connects the capacitor to the bit line through the access transistor that's turned on. Now charge sharing happens. This capacitor shares this charge with the bit line over here. So this becomes slightly perturbed. This becomes VDT over 2 plus delta, and this becomes minus delta. That plus is a bit incorrect over here, but that's fine. I think you get the point over here. And because of this perturbation, what happens is sense amplifier gets turned on, and it starts amplifying the difference between the two ends of the cross-coupled inverters. So it amplifies the difference. The bit line becomes VDD. Essentially, it takes the value of the source cell, and the other side of the sense amplifier becomes 0. Now we've captured the value that was in the source cell, right? It was VDD. Now sense amplifier sees that it's VDD. Now the next step in activation is really restoring the charge. Because of charge sharing, the sense amplifier is very strong. It's huge, actually, compared to each of these cells. As a result, it drives the charge back into the capacitor. So the capacitor gets replenished with full charge. So all of this becomes VDD in the end, because the initial starting point of the source cell was VDD, meaning charge state. Okay, we've captured the data in the sense amplifier now, as well as the bit line. Now, the next step in RowClone is to transfer this data into the destination cell. To be able to do that, what we do is we disconnect the source row from the bit line, and we connect the destination row with another activate to the bit line. Now, once you connect the destination row with another activate to the bit line, now you guessed what happens probably. Charge sharing again happens. This is high voltage. This is low voltage. Charge flows from high voltage to low voltage and fills the capacitor, because sense amplifier is very strong. Okay, that's the idea basically. Now we've copied the value of the source row, which was VDD, into the destination row, which now became VDD also. That's the idea at a bit level, basically. And this operates based on charge sharing principles completely, as you can see. There's nothing magic about it. Okay, so now we know exactly how this works. We activate the source row, which copies the data into the source from the source row to the row buffer. And then we activate the destination row by disconnecting the source row from the row buffer and connecting the destination, which enables copying of the data from the row buffer to the destination. 2 consecutive activates, basically. And this is the core of the idea. This leads to an order of magnitude reduction, more than an order of magnitude reduction in latency. And as I said, 74x reduction in DRAM energy, which is significant. There's no DRAM bus bandwidth consumption, very small changes to the DRAM chip. And as I will show in the historical perspective that I will give you, later works have shown that you can actually do it in some real DRAM chips without even changing the DRAM chip, by modifying the timings in the memory controller such that you can imitate 2 consecutive activates. I think this is actually quite fascinating that you can do it in off-the-shelf DRAM chips. Not all of them, but many of them have the capability. So proof of concept exists in real systems 6 years after this paper was published. Okay, there are clearly constraints to this fast parallel mode that operates at the row granularity. First of all, location of source and destination both should be in the same subarray. Basically, source row and the destination row should really share sense amplifiers for this to work. If they don't share sense amplifiers, this doesn't work, clearly. That's why the paper develops other mechanisms to copy data. And also, there's a size of the copy problem, which is now you have to copy all the data from the source row to the destination, because activation and sensing operate at the row granularity. Clearly, if your copying granularity is smaller, then you have a problem. If your copying granularity is larger, you need to break down the larger copies into these smaller row level row granularity copies. So granularity is always an issue actually in this sort of approaches, in memory processing approaches. It's also an issue in existing CPU designs, right? What's the granularity of a cache line? What's the granularity of an operation? But granularity becomes problematic as if your granularity, if your basic granularity is very coarse grained, like 4 kilobytes, right? That doesn't sound good potentially. So these are constraints. These are also the downsides of the fast parallel mode. So the paper proposes mechanisms for interbank copy as well. Let me quickly describe it. Remember the shared bus between the banks? We have a shared internal bus. This could be only 64 bits, for example. It's not very wide, but it's on the DRAM die. You don't need to go off chip for this. So the idea is, if you want to, let's say, copy 3 64-bit elements from this row in this bank to this row in this bank, you can do it internally by pipelining. Basically, you set this bank to read mode, you set this bank to write mode, and you basically tell, memory controller tells the DRAM chip to copy n number of 64-bit elements from here to here in a pipeline manner in the shared internal bus. That's the idea over here. Again, most of the mechanisms that require this are already existing in the DRAM chip. You can read from a bank, you can write to a bank, except you cannot do it internally under a memory controller's direction today, because you cannot set this bank to read mode and write mode at the same time and connect things this way. You just need to have the mechanisms to be able to do that. So this requires a little bit more hardware cost, but again, it's not too much hardware cost, because fundamentally reading from a bank is possible, writing from a bank is possible, interconnect is there. You just need to add the controls and necessary additional logic to enable this sort of transfer that can be done internally. Now, the good news is you can do it at the 64-bit granularity over here, right? The granularity is not a problem over here, and you can do it interbank. But the bad news is clearly you're going through some interconnect to go from one bank to another over here. So the benefits are going to be lower than the fast parallel mode. So, and that's the benefits basically. You can overlap the latency of the read and write. And as a result, the paper shows that you can reduce the latency of a 4 kilobyte copy by almost 2x, and the energy of a 4 kilobyte copy by 3.2x, which is not bad actually, because we're talking about 4 kilobytes over here. In fact, if the granularity is very low, this could still be very beneficial. Okay, so let me generalize it basically. So if you want to do it inside the subarray, you have 2 consecutive activations. If you want to do it across different banks, you have the interbank copy mechanism that we described, pipelined internal read or write. Now the question becomes, what if you want to copy data from one subarray to another subarray within the same bank? This is the troublesome issue in the paper. Basically, there's no path that directly connects this subarray to this subarray. They really don't share the sense amplifiers, and they don't share, well, they share the bank IO, but that's just IO circuitry. So the paper proposes to use interbank copy twice, meaning if you want to copy one row from this subarray into another row to this subarray, you first copy the source row to some other bank using the interbank copy once to a dummy row, and then take that dummy row that has the copy data and copy it into this subarray. So you use interbank copy twice. As a result, you do not gain much in this case. I'm not going to talk about that in detail, but you will see. And later works have improved, especially in inter-subarray copy as well as interbank copy. So the area cost of all of these mechanisms, the paper evaluates them to be 0.01%, which is quite low. Okay, so that was all copies, right? The paper talks about initialization. What is initialization? Initialization is just a special case of copy. basically the paper says zero initialization happens a lot in systems. In fact, operating systems, for example, when they release a page, they initialize the page to 0. Some programming languages require data structures to be initialized to zeros. So zero initialization is quite common. So the paper proposed an idea saying, why don't we fix a row at 0? And if you do it in an optimized way, you don't even lose a lot of capacity, 0.5% loss, but you can actually optimize even more. And if you actually have a row fixed at 0, you can just copy it using fast parallel mode to another row in the same subarray, right? Very quickly. Or you can actually use any other mode that we discussed in RowClone to copy it from one subarray to another subarray or to another bank as well, right? That's the idea. Okay, so basically, this is zero initialization. This is the most common. The paper proposed reserving a row in each subarray, always 0, and copy data from the reserved row into the other rows in the same subarray. And you can see the benefits are significant over here, and the loss in capacity is very low. But you can also initialize with arbitrary data. You can initialize one row and then copy the data to the other rows with arbitrary data, right? That's also possible. Zero initialization is most common. That's why the paper proposes some support for it. Okay, so this is a summary of the latency and energy benefits of RowClone as it's proposed in this paper. Clearly, intra-subarray copy provides the highest benefit, highest latency reduction, energy reduction. If you do interbank, you still gain benefit in terms of latency and energy. Inter-subarray copy, because you have to go through one other bank, the benefits are not significant in terms of latency, but you still gain in terms of DRAM energy, as you can see, but not as much. So, of course, zero initialization incurs significant benefits also, as you can see, 6x, 45.5x. It's lower than copying because initialization just writes data, right? You don't need to read the data and then write it. So the benefits are lower because the cost of initialization is lower to begin with. So you can see that this is quite significant. And as I mentioned, later works improved the interbank and inter-subarray copies significantly, almost to the levels of this one, not quite exactly, but you will see that when we talk about it. I'll refer you to some papers. Okay, all this comes at very low cost, very little increase in die area. So of course, very low cost in terms of die area, but there's some cost in terms of system design. If you want to really take advantage of an idea like this, you really need to design the system to enable it. So your DRAM may be RowClone capable, but your application needs to take advantage of it in the end. So you really need an end-to-end system design to enable this. And the paper talks about multiple different issues. How do you communicate occurrence of bulk copy initialization across the layers from the application into the DRAM? How do you ensure cache coherence? The paper talks about that. How do you maximize latency and energy savings? And how do you handle data reuse? So the paper actually covers all of these, and all of these are actually issues in DRAM computation, not just RowClone. RowClone is actually a very simple baby step example for doing in-DRAM computation. I don't want to even call it in-DRAM computation, but in-DRAM data movement. But it suffers from all of the issues that you suffer from in-memory computation. And the paper realizes that early. Okay, so let me quickly go over what the paper proposes. Hardware-software interface. The paper adds 2 new instructions, memcopy and meminit, into the ISA. But some existing ISAs already have these instructions, for example, x86. And you can read the paper for more detail. And you need to have microarchitecture implementation to execute these instructions, of course. And the microarchitecture needs to check if the instructions can be sped up by RowClone internally. And it can export or offload the instructions to the memory controller if RowClone is implemented in the DRAM chips and the memory controller. So this is hopefully simple, but you need changes in the hardware-software interface if your ISA doesn't support it. Managing cache coherence is a more hairy issue. So RowClone modifies data in memory, and you need to maintain coherence of the cache data. There might be some data that's in the cache, and you're copying into it, right? What do you do, basically? So the paper handles it in a practical manner, let's say. It's similar to the direct memory access engine. Source and destination are in memory, and you can leverage the hardware support that existing DMA engine, direct memory engine, access engines support. Basically, you need to flush the destination row and the source row into the memory before you do the RowClone operation. This may take time, but this is the most practical approach. Later works have proposed mechanisms for in-memory computation cache coherence that this paper also can take advantage of, but I'm not going to go through that. This paper was one of the earliest ones to realize that you could actually use DMA for this. And there are additional optimizations that the paper provides that I'm not going to talk about also. The third issue, how do you maximize the benefits? Maximizing the use of the fast parallel mode. And the paper basically suggests we should make the operating system subarray aware. Basically, if you make the operating system subarray aware, the operating system, whenever it's copying a page to another page, it can basically allocate the destination page in the same subarray as the source page, right? For example, the operating system has copy on write or box zeroing primitives. If the operating system knows where the data is placed, which subarrays are there in DRAM, and where it has allocated the data, it can allocate the destination page in the same subarray as the source and use fast parallel mode to copy. And usually this copy on write is done lazily. Whenever you write to the source page, that's when you actually do the copying to the destination page, or the destination page, I should say. Okay, box zeroing is similar. You can use fast parallel mode to copy data from the reserved zero row if the operating system knows the subarray structure of DRAM. So this requires some, of course, work to expose the subarray structure of DRAM to the operating system. But I think this is a very promising direction going into the future to optimize systems in general. Subarray-aware system design is what I call it, and I like this a lot, actually. There's a lot more that needs to be done in the system for this. And finally, there's another issue of handling data reuse after zeroing. You've zeroed a destination row. What if you need to reuse it? This becomes a bit interesting. Basically, the paper realizes that there are two phases over here. The operating system zeroes out the page, and if you do initialization, and the application uses cache lines of the page. There are two phases. So RowClone is good at avoiding misses in phase one by doing it inside the DRAM, but it incurs misses in phase two because it doesn't do update the cache. And the paper has a small fix to this problem, which actually is quite practical and effective, which is called RowClone Zero Insert, RowClone ZI. Whenever you're copying data inside the DRAM, you also insert zero cache lines into the cache. So for example, if you actually are, let's say, if you're updating a 4 kilobyte page and zeroing it, update also the cache lines, write zeros to the cache lines associated with that page inside the last level cache, for example. Now, this makes sense. This is also interesting, but there could be other optimizations. That the paper does it with some optimization, but you can also do a prediction in terms of when a page or which cache lines are going to be used, and do it based on the prediction mechanism. The paper doesn't go into those complicated mechanisms. The paper proposes a simple heuristic. Clearly, there's room for future work. So I've given you some results of the paper, but there's more application level results in the paper as well. The previous results were at the copy granularity, right, and initialization granularity. Now let's take a look at the methodology and evaluation of the paper and provide the key results, application level results. To study application level benefits, the paper uses an out-of-order multi-core simulator, and you can see the parameters. I'm not going to go through the details of it. It uses 6 copy and initialization intensive applications and spec CPU 2006 for multi-core, and it evaluates performance using multiple metrics, instruction throughput, as well as weighted speed up. I'm not going to go into the details of it. This is basically standard methodology in evaluating multi-core speed up and also single core speed up. And these are some interesting applications that the paper tests, because we found out that existing applications, a spec suite, for example, standard suites, don't do a lot of copying. Even though we know that this is a big problem, as we will also discuss again, standard suites don't have workloads that exercise this problem. So we actually cooked up or came up with real application scenarios like system boot up, compilation, forking, memcached, MySQL, shell script, different examples that do a lot of copying and initialization at different levels. And these are the applications, as you can see. Oh, sorry. And this is the breakdown of the memory traffic of each of these applications. So they have substantial amount of zero initialization and copying. And different applications have different amounts, as you can see, and different types, as you can see. Forking, for example, needs to copy on write. And depending on how much amount of memory you're going to copy, it could actually be a large fraction of the memory traffic. And the paper actually analyzes forking in detail. This is kind of the poster child, if you will, for this paper. But there are other applications that are clearly important also, like shell script is heavily intensive in both copy and initialization. Okay, the paper evaluates the benefits of RowClone in terms of single core performance and energy. And basically, it sees that there's significant performance improvements, instruction per cycle improvements, and there's significant memory energy reduction, as you can see. I'm not going to go into details, but improvements correlate with the fraction of memory traffic due to copy and initialization, because you're optimizing copy and initialization. If copy and initialization are a big bottleneck, like in fork bench or the shell, you get higher benefits. If the copy and initialization are a smaller bottleneck, you get lower benefit, but still significant benefits, as you can see. Okay, on multi-core systems problem becomes even more important, because whenever you do the copy inside the memory, you're saving bandwidth on the memory bus. So another application can now access memory bus, whereas it couldn't have before, right? Because it would have been delayed because of some application doing initialization or copying. So bandwidth savings on the memory bus benefits all applications. And the paper's results show that actually. So to be able to demonstrate that, the paper shows runs copy and initialization intensive applications with memory intensive spec applications. Half of the cores run copy and initialization intensive applications, remaining half run spec applications. So this is one methodology, of course. In fact, you could poke into this methodology and say, oh, maybe that's not a realistic scenario. But then the question becomes, what is a realistic scenario? The paper does some reasonable effort to actually try to evaluate this, basically. Okay, now let me show you the results. The results are good, basically. Overall, system performance improves significantly across 2-core, 4-core, and 8-core simulations. And performance improvement increased with increasing core count, according to the paper. And memory energy efficiency also improves significantly. And there's consistent improvement in energy per instruction, as you can see. And the paper analyzes all of this. The paper also analyzes fairness to different applications, which I'm not going to talk about in this. So it also shows that fairness improves in the system because an application's memory access request does not get delayed behind a huge number of requests due to page copying and page initialization. Basically, you're reducing the load on the bandwidth, and you're also improving the quality of service and fairness that applications experience. This sounds good, right? This sounds like a good technique that improves both performance, energy, quality of service, and fairness by reducing the memory bandwidth bottleneck due to data copy and initialization. Okay, so I think I'm done with the summary almost. Basically, let me summarize. Bulk data copy and initialization is the problem that's targeted by this paper. They cause unnecessary data movement on the memory channel, which degrades system performance and energy efficiency. And the paper proposed the new idea of RowClone, performing copy in DRAM with low cost. The key idea is to use a row buffer to copy large quantities of data from the source row to the destination row. And in the best mechanism, it leads to significant latency and energy improvements for 4 kilobyte bulk data copy. And the paper shows that at the application level, you can extract copy on write and bulk zeroing with significant performance and energy efficiency improvements with little overhead and DRAM chip area. And the paper touches on a lot of issues related to RowClone, as I have discussed, but there are more issues that are discussed in the paper than I have time for. Okay, so that is the summary, and I think I've done a reasonable job finishing it in 20-25 minutes. I didn't time myself, but hopefully that was close enough. I gave you, of course, some anecdotes, etc., that you normally wouldn't do if you were not me, for example. That lengthened it a little bit more. Now let's go into, first of all, any questions so far? If there are questions, yes, there's some question in the room. So I think you will need to get the, what is that? The ball or the microphone. I don't know what the microphone looks like over there. Yeah, it's a real microphone today, not the. Yeah.
Okay, sure. Okay, so I have one question regarding the charge mechanism, and it is whenever we have when we activate the row we want to copy from, the bit line has the new value, and then we close that row and open the other row, and then that value gets copied into this destination.
That's correct. Yes.
Okay, but how does the bit line get reset? Right, like, but this is like even a.
Oh, okay, I see. At the end, basically, you need to do a pre-charge. So you reset it at the end. Yeah, you still need to do a pre-charge. I didn't cover that, but yes, it's no different from activating and pre-charging afterwards.
Okay, thank you.
Okay, sure. That's a very good question. Thanks. Okay, any other questions? But this is the right time to ask this sort of questions, basically. If you have a question on the mechanism of the paper or the evaluation of the paper, etc., it's always a good time to ask questions before we go into strengths, weaknesses. Some of these issues we may also cover in strengths and weaknesses, but feel free to ask questions so that we can have good discussion, regardless of wherever you are. So if you're on Zoom, please also ask questions. I see a lot of people on Zoom. Okay, yeah, I think somebody else is going to ask questions. Go ahead.
Can you hear me? Okay.
Yes, yes.
I wasn't sure if this was exactly the same question, but or if I misunderstood it. So if you first get the value from the source row to the row buffer, how is it? Is there a mechanism, or what is the mechanism that not accidentally the value that was previously in the row buffer gets copied to the?
Oh, okay. Yeah, basically that's. Let me go back to that slide. Actually, I think it's a very similar question, I would say, but I think you asked it in a different way. So basically, if you look at this picture, you initially start out with VDD over 2 on both ends and the row buffer. This is called the pre-charge state in DRAM. So this is neutral, as you can see, right? That's how you can sense the value. So after you're done with the RowClone operation, you need to go back to this state by pre-charging the bit line. And there's a separate process I'm not going to go into right now, how that pre-charge is exactly done, but it sets the bit line to VDD over 2 on both ends of the sense amplifier without touching the data values over here. Does that make sense?
Yeah, okay, thank you.
Okay, good. So you always have to, if you want to really sense something in a DRAM cell, you always have to set the bit line to this state to begin with. Okay, cool. Okay, now I'm going to go back and feel free to ask questions. Otherwise, I'm going to move on to the analysis. Okay, I guess I don't see any questions anywhere, so I'm going to move on to the analysis. So next step is really analyzing the paper. Now you're the presenter. You want to first cover the strengths of the paper. And every paper has strengths, basically. So you should be generous to the paper, let's say, even if it's a terrible paper. Well, I think this is a great paper. I'm not saying it because I wrote it, but I think it has a lot of good sides of it, but we will see the bad sides of it also, as you will see soon. But basically, strengths are also ordered in terms of importance. Basically, the most important strength comes with the conceptual novelty, etc. Right? So the idea, basically. So this is basically a simple, novel mechanism to solve an important problem, in my opinion. It's effective and it leads to low hardware overhead. It's an intuitive idea, in my opinion. Hopefully you agree with that. It's actually surprising that no one has proposed something like this. I will mention that later on, but no one has actually proposed something like this. Let me see if my light is going to turn on. I don't know. It's not listening to me, but as long as you can see me, it's fine, I guess. Okay, it greatly improves performance and efficiency, as you can see, but assuming data is mapped nicely, as we have discussed also, and this is going to be a weakness as well. It seems like a clear win for data initialization, right? If you actually want to initialize bulk data, you don't even care about the mapping, right? You basically initialize 4 kilobytes a page. You just do it, right? Because you can do it inside a subarray. Make software designers' life easier, because software designers usually tackle the issue, or always they need to actually solve these data movement problems. And now you're actually getting rid of some data movement, page copy, and page initialization overheads from software designers' life. For example, if copies are 10x to 100x cheaper, how do you design software? There's a lot of work that looks at zero copy systems. Maybe there's a much better way of designing software with RowClone. And I think this is actually the bigger, higher level implications of the issue that this paper clearly doesn't tackle, right? You cannot solve the entire system software design with one paper, but I think implications are enormous. And paper tackles many low-level and system-level issues at the same time. This is an interesting paper that's not just at the circuit level, that's not just at the architecture level, that's also at the system level, basically. It spans a lot of dimensions, let's say, in the layers of transformation. And I believe it's a well-written, insightful paper. You can also take a look at it yourself, of course. But I'm trying to evaluate this without bias, of course, because you'll see that in the weaknesses also. Okay, so, and also I think maybe in hindsight, most importantly, the mindset of the paper has been very influential, basically. The mindset is that memory is an accelerator. Memory has some good capability to do acceleration of certain operations, and data copy and initialization are two of those operations that the memory can be extremely good at accelerating. So we're designing all of these accelerators. Why not also have some specialized accelerators in memory? And it's similar to a conventional accelerator from that perspective. It's different from the conventional accelerator from the perspective that it's really getting rid of the memory bandwidth bottleneck. All of the conventional accelerators on the processor side are actually bottlenecked by memory bandwidth, which this paper is trying to solve. But programming issues are similar to the conventional accelerator, if you will. Okay, it also has changed the mindset, basically. It basically started the mindset of minimally changing DRAM by doing processing using DRAM inside the DRAM. And it showed that DRAM has great capability to perform bulk data movements. And later works built on it to show that the DRAM also has great capability to do computation internally with small changes. So RowClone is really first example of this. It showed that you can exploit internal connectivity inside the DRAM with some orchestration to move data between different DRAM parts, as well as to initialize data. And later works showed that you can actually exploit analog computation capability. So here we're also exploiting analog chart sharing capability, right, as well as internal connectivity. So this is the RowClone is actually the first one in a series of works that I've shown that, both from my group as well as other groups. Okay, that's strengths, I think. That's good. Now let's take a look at the weaknesses. This is where you really need to be critical and draw out the weaknesses. And I've given you some examples of the weaknesses while I was talking, but now let's put them together. It's always good to start with conceptual weaknesses. Now, I think here there's no conceptual issues with the paper, so you will be hard pressed to find any conceptual weakness. If you find it, let me know, of course. So there are mechanism weaknesses as a result, meaning you may not be able to take advantage of it if your data is not mapped to the same subarray to deliver the largest benefits, right? Clearly, this is a weakness. You need to do something else in the system to take advantage of the best mechanism. Okay, I see a question over there. Please go ahead.
With conceptual weak. Oh, is it muted? Okay, yeah. So can you maybe explain what the?
Okay, sure. Yeah.
With conceptual weaknesses, what do you mean with that?
Yeah. Okay, I will explain it. Basically, I mean, it's not. I don't have an example for it right now, but for example, if the paper claims that something is a problem, but it's not a problem, right? Meaning that's a conceptual weakness, right? Or if the paper proposes a mechanism, and if the paper describes it, but you find out that the mechanism actually doesn't work, right, as described, that's a conceptual weakness. Does that make sense?
So it's basic. So already the assumptions are kind of broken. Exactly.
That's what I would say. Basically, that's a big problem with any paper.
Okay.
It should have an. And this happens also. I mean, even with published papers, it happens. Sometimes these papers get eliminated in their review process, but not always. We will talk about the review process at the end of this lecture, hopefully. So you will get some insights. Okay, I don't have a good example of it right now, but maybe some of the papers we cover will have some similarities to that, right? Or, yeah, okay, I will not give an example right now because that will derail us a little bit. Okay, very good question though. Okay. So, okay, basically this weakness, basically the RowClone helps less if data movement is not within a subarray, right? Clearly the results show that also. In a sense, the paper acknowledges it, but it's still a weakness, right? The mechanism requires some mapping, some more effort from the user, programmer, system designer. And certainly it does not help if data movement is across DRAM channels, right? This works only if the data movement is within a DRAM chip. If you have to move data from one memory controller to another controller, that's a separate problem. Okay, inter-subarray copy is very inefficient, as I have shown you. It doesn't provide you performance. It provides you some energy benefits, but not a lot. And we're going to solve that. Later work is going to solve that clearly. It caused many changes in the system stack, and clearly that's a criticism and that's a weakness. Ideally, you would get all of these benefits without any change in the system stack, but as I said, all in-memory computation mechanisms will have this problem. So end-to-end design spans applications to circuits. It is a weakness at some level. It's hard to argue that this is a strength. This is what we need to do in existing systems to get high benefits. But if we could get it without all of those changes that we do across the system stack, it would be even easier to adopt, right? So software, hardware, cooperative solution might not always be easy to adopt. Okay, cache coherence and data reuse cause real overheads, and the paper acknowledges this, but still there are weaknesses. Evaluation is done solely in simulation, and that's also a weakness, clearly. But again, it's not a large enough weakness because not all works have to be evaluated in real systems, right? In fact, it's very difficult to evaluate this idea in real systems if you do not have the infrastructure. We will later see some work building on top of this work that evaluated the idea in real system and showed the proof of concept and actually proved the validity of the RowClone idea, let's say. I'm going to mention that. Evaluation doesn't consider a multi-chip system. Now we're getting into the territory of rat holes. Basically, you can always poke to evaluation, right? Evaluation doesn't do this, doesn't do this. The workload formation is not representative. So you can go into a lot of rat holes over here. Are these the best workloads to evaluate? Is this the right mix of workloads, etc.? Okay, I'm going to stop here, but you can see that you can actually list a lot of things in the evaluation, right? Why didn't you evaluate DDR4, etc.? DDR4 was not very popular at the time the paper was published, for example. But you could poke a lot of holes into evaluation, but in essence, they're not as fundamental as concepts, mechanisms, etc. So basically, my suggestion to you is try to avoid the rat holes. Try to find the bigger weaknesses. So clearly, these are weaknesses that are independent of the workload or evaluation, but these are weaknesses that are solely evaluation and workload based. So they're more closer to the rat holes over here: workload, metrics, configuration, and details. Okay, now let's go into thoughts and ideas building upon this. Any questions so far? Strengths and weaknesses? These are important, clearly. But now the next step is going into thoughts and ideas building upon the paper. So improvements on RowClone. This is, I mean, bigger discussion. And feel free to actually interrupt me with discussion points, but I'm also going to give you a historical perspective since we've done research in this area initially since RowClone was published. But basically, you can ask many questions. And maybe you're asking questions. Feel free to ask them. I'm going to help you a little bit. Can this be improved to do faster inter-subarray copy? Clearly, inter-subarray copies are a weakness of this paper. And the answer is yes. I'm going to talk about the Lisa paper quickly. One of my PhD students in his next PhD thesis solved this problem, basically, as we will see. Can we enable data movement at smaller granularities within a bank? Can we solve that granularity problem? Yes, a recent paper actually does that. I'm not going to talk about that in detail. Can this be improved to do better interbank copy? So interbank copies are also lower performance and lower energy improvements compared to intra-subarray copies. And yes, there's a recent paper on that we wrote also. Can similar ideas and DRAM properties be used to perform computation as opposed to just data copy and initialization? And the answer to that also is yes, basically. Vivek, who was the first author of this RowClone paper, also developed these mechanisms. And I'm going to mention these also just to give you a full historical perspective, let's say. And of course, in your presentations, if you can give this sort of perspective, that's always good. But don't take as much time as I'm going to take, because at this point, I'm going to kind of be more educational as opposed to giving an example of a presentation in this lecture. But hopefully your discussion points can raise all of these questions, right? You can do exactly what I did over here. You can ask these questions, these weaknesses, have they been improved? And you can also answer them saying, yes, there's this next work, there's this next work, there's this next work, there's this next work that came after this. And here you need to do some research, of course. Your mentors can be helpful to you to find out this research. But this slide is something you can also construct based on the paper that you review. Okay, now let me give you some cool ideas, let's say, on improving upon RowClone. So remember that one big weakness of RowClone was actually inter-subarray copies, right? RowClone was not good at inter-subarray copies. And this paper by Kevin and co-authors improves inter-subarray copies. So let's take a look at this. So it's motivated by the same thing, moving data inside the DRAM. So if you look at subarrays, it could be 4 kilobytes, 8 kilobytes, whatever it is. And each subarray is 512 rows. And if you want to move data from one subarray to another subarray, you're stuck, basically. You need to go through the internal data bus between the DRAM banks. So basically, you have low connectivity in DRAM. This is abstracting it a little bit, basically. An internal data bus is not between the subarrays, but it's between the DRAM banks, but you can use it also from moving data from one subarray to another one. But basically, we have low connectivity in DRAM, and that's really the fundamental bottleneck for bulk data movement in a general sense across all parts of a DRAM chip. Within a subarray, we're good, but across subarrays, we're terrible as RowClone. And this paper targets that low connectivity problem. And the goal of this paper is to provide a new substrate to enable wider connectivity between subarrays, not within a subarray, but between subarrays, because within a subarray already exists. And the idea is called low-cost interlinked subarrays. And as you can guess, we're interlinking subarrays. And it enables fast bulk data movement between subarrays. You have wide data path between subarrays via isolation transistors, small changes to DRAM chip area, but larger than RowClone, as you can see. So the key idea is this. If you have subarray 1 and subarray 2, normally they're not connected to each other today. The paper basically adds connectivity, isolation transistors, and you can actually control those isolation transistors. Whenever you want to move data from this subarray to this subarray, you enable these isolation transistors. Now it looks like as if you have a longer bit line that's spanning multiple subarrays. And then you can move data from one subarray's row to another subarray's row buffer. And then you can move the data from that subarray's row buffer to that subarray's row, one of the rows in that subarray. So I'm not going to go into more detail than this, but this is the key idea. And it's a beautiful conceptually, right? It's increasing the connectivity by a small amount, but it's actually quite powerful. In fact, it's so powerful that it's not just used for data movement. It's used for other things, as I will describe, as the paper describes. So clearly, it speeds up fast bulk data copy between subarrays. So the copy latency between subarrays improves by almost 9x, as you can see. Remember, RowClone inside a subarray improves data copy latency inside a subarray by 11 point something x. So this is close enough, not terrible, basically, in the same order of magnitude almost. And this leads to significant speed up and energy reduction in applications that this paper studies. But this also leads to in DRAM caching. For example, one subarray can cache hot data, let's say. It could be smaller, it could be faster, and it can move the data dynamically from this subarray, hot data from this subarray to this subarray, such that if the data is hot, you can always access the faster subarray, let's say. You can have heterogeneity inside the subarrays. And this leads to significant speed ups, as you can see. And you can also have fast pre-charge latency. Pre-charge is the operation that sets the bit line and the sense amplifier to VDD over 2. Now, if you're connecting this subarray to this subarray, you can also connect the pre-charge units of this subarray to this subarray. As a result, you can use multiple pre-charge units to pre-charge every single subarray, which reduces the pre-charge latency significantly. So you can see that this paper was initially motivated by solving a problem that RowClone has, inter-subarray copy, but it actually ended up solving multiple issues in DRAM, which is actually always a good thing. It's a versatile substrate in the end. Okay, if you want to learn more about Lisa, you can certainly read the paper and you can watch some of our computer architecture lectures if you're interested. So as I said, other problems have been solved by other papers. Figaro, for example, does finer grained in DRAM data relocation and caching, which is actually a cool idea also. It basically uses the peripheral circuitry, global I/O inside the DRAM bank to do the copying in a fine-grained manner, but I'm not going to talk about that. And this uses the logic layer inside the memory to actually do a better interbank copy and do parallelization between interbank copy and accesses, which actually is a downside of RowClone that's mentioned in the paper. Whenever you're copying data from one bank to another bank, you cannot access the other banks. You cannot start accesses to other banks, basically, in RowClone. This paper solves that problem, for example. And, okay, later papers also develop other mechanisms. This is Vivek's later paper that basically showed that by exploiting the chart sharing principles in DRAM, you could do more than just copying and initializing data. Basically, you can do bitwise and OR. And this is the more general version of that paper, which shows that you can do bitwise and or not, which is functionally complete. So you can actually map any algorithm with some effort, of course, to the substrate. And this is another paper, and this is another paper that actually eases that, as you can see. So RowClone actually has led to a lot of research in in-memory computation as well. If you want to trace back the early parts of that research, it's really RowClone to begin with. Okay, so basically that's what I'm talking about. Let me ask the questions again. Can this idea be evaluated on a real system? How? Yes, later work has done that. I'm going to talk about the Compute DRAM paper, hopefully. They've basically shown that on off-the-shelf DRAM chips, you can do it by just modifying the memory controller. Can similar ideas be used in other types of memories, phase change memory, RRAM, STT-MRAM? Yes, there's a paper that came afterwards, as you can see 3 years afterwards, that showed that. Can the chart sharing properties be used for other functions, not just and or not and copying, but other functions? And yes, there's a variety of works that propose generating random numbers and physical unclonable functions like signatures in DRAM that basically are inspired, let's say, by this sort of chart sharing principles in DRAM. And then there may be other questions that you ask. Can we have more efficient solutions to cache coherence, data reuse, and other works actually cover that, but I didn't get a chance to write them over here. The Conda work, for example, in ISCA 2019 looks at cache coherence and minimizing its overheads. But let me talk about some of these works. This is Pinatubo. Basically, it shows that you can do RowClone and phase change memory. You can also do bitwise operations. I'm going to talk about that more when I give you the even more historical perspective, let's say. And this Compute DRAM work is very interesting because it appeared 6 years after the RowClone paper and 2 years after the Ambit paper, 4 years after the bitwise AND and OR paper. And they basically showed that by modifying the timings in the memory controller, you can imitate back-to-back activates like RowClone, and you can actually do RowClone in existing memory chips in a substantial number of rows. But because the chips are not designed for this purpose, you cannot do it in all of the chips reliably. But you can see that by violating the timing constraints such that you get the second activate as close as possible to the first activate, you can see RowClone, row copying in a good number of chips. So this shows that chips are fundamentally capable of doing it, even existing chips, without modifications. So it's always good if later work actually validate your ideas, and it's good to give that historical perspective also to you, if you will. And if you actually, for example, uncover such later works when you present your paper by the help of your mentors, for example, or if you do it on your own, that's always good. Is there a question in the room? Yeah, I think there's a question. Please go ahead.
Yeah. You mentioned that you can use most of the off-the-shelf DRAM chips, but it's not 100% reliable because they're not built for that. Did you look into, or did they look into what has to be changed manufacturing-wise to make it like 100% reliable?
Yeah, so that's a good question. This paper did not, because this paper really doesn't talk about. Basically, the goal of this paper is to demonstrate that some of these older ideas, like RowClone and Ambit, are doable in existing DRAM chips with modifications to the memory controller. Their goal is not to make them reliable in future chips. So if you really want to, the answer to your question exists in the RowClone paper, actually. The RowClone paper is designed for reliability, but this paper doesn't go back and circle the gap, let's say, in existing systems and the RowClone.
Okay, thank you.
But that's a very good question. Okay, wait, I'm going backwards. Okay, so now let me finish with takeaways, and I'm going to give you even more historical perspective, and feel free to actually ask questions and initiate any discussion. So I think the key takeaway from RowClone is that it's a novel method to accelerate data copy and initialization. It's simple and effective, hardware software cooperative, good potential for work building on it to extend it, and clearly we've seen a lot of work that built on it, even including work that has shown that it can be done on a real system to some extent. Of course, not exactly how we envisioned it, but to some extent you can exploit the same principles to get some of the benefits, and also to different granularities to make things more efficient and effective. And many works I've already built on the paper, as I've said. These are some subset of the works that I mentioned. There are a lot more works you can find online, and if you find some interesting ones, please let me know. And I think it's an easy to read and understand paper, and I think this is really important when you evaluate a paper, and also better yet when you write a paper. It's really important to make it easy to read, easy to access, easy to understand, in addition to covering a lot of issues. And this is not an easy task, of course. If you want to reach a wide audience with a technical paper, or even with a non-technical paper, you should really make it easy to read. Of course, technical papers are harder to make easy to read compared to non-technical papers, right? As I mentioned, mindset is important, and the RowClone is actually changing the mindset such that, okay, memory can be an accelerator also. In fact, it could be a very powerful accelerator by getting rid of the memory bus bottleneck, bandwidth bottleneck, and specifically for data copy and initialization operations. And as I said, it is perhaps the first modern work that has shown that DRAM has great capability to perform bulk data movement initialization internally with very small changes. And later works built on it, as I discussed. Okay, now after this point, the next step is really open discussion. People can ask questions. I have some agenda, of course, and you should also have some agenda when you're presenting a paper. I mean, this is a generic thing, of course. Basically, you can always ask these generic questions, right? What are your thoughts on the previous ideas? How practical is this? Well, I think based on what I described, this is quite practical. Will the problem become bigger and more important over time? I think I will answer this. It will become bigger and more important because memory bandwidth bottleneck is becoming bigger as we put more processing units to access memory, and memory bandwidth is not scaling very well. And also applications are becoming increasingly data intensive and data movement intensive, as we've discussed multiple times. Will the solution become more important over time? Likely, yes. Are other solutions better? Well, there are new solutions, of course, that improve upon RowClone. They're better, as you can see. But maybe there are some other solutions that can be better. Who knows, right? As far as I understand, and I know about DRAM, the fast parallel mode introduced by RowClone is very hard to beat. Can you do better copies, for example, inside a subarray? That's always a good question to ask, but that's a tough problem. RowClone has raised the bar significantly, basically. And then is the solution clearly advantageous or the opposite in some cases? And I think it's clearly advantageous in initialization, right? Data mapping is not as big of a problem in initialization. Okay, there's some comment or question in the room. Please go ahead.
So, from my understanding, we need the operating system to support this, right? It needs to know. So usually we want to use the fast parallel mode because the intersubarray is kind of useless, to say it in rough words. But then this would require us to keep a lot of data, doesn't it? And so this is a weakness which you mentioned, but I don't think that it's just a weakness, because we need to actually make sure that, first of all, the operating system needs to know like which subarray is where. So we need to keep a data structure, being able to query, okay, what kind of subarrays can I access, right? So
yeah, exactly.
And doesn't this like have the possibility of introducing such a big overhead that it actually kills off the gains. For example, it queries the data structure. Data structures, nope, there's nothing available. So now we got to do the slow copy, and at the end we actually reduce the speed and so we increase latency.
Okay. Let me first correct something that you said. Basically, if you do the slow copy, you don't reduce the speed, right? It's on par with what we do today with the intersurvey. So you don't lose anything, let's say, but you don't gain as much. Let me correct that. You gain in terms of energy, but again, as you said, it's not that much, unless you employ some of the later ideas, right? Like Lisa. I think there are multiple. So I think in the general purpose computing sense, you're right. It requires operating systems to be more, let's say, intelligent from my perspective, more aware of the hardware topology of DRAM. There's another way of, I will first enter it from a special purpose perspective where you don't have an operating system, like a machine learning accelerator, for example. You have your dedicated DRAM or a GPU where you have a lot more visibility into your DRAM. I think it's a lot, this sort of ideas are a lot easier to adopt in those systems where you don't have to go through an operating system to process data. For example, if you have a machine learning accelerator, maybe your compiler needs to be aware of the subarrays, yes. Maybe not, maybe the application programmer needs to be aware. Somebody needs to be aware, for sure, no question about that. Subarrays need to be exposed to get the maximal performance, but maybe it doesn't need to go through the operating system. Again, you could argue that, yes, that's overhead. Yes, absolutely. I mean, someone needs to do it, right? Someone needs to be aware. In the general purpose case, yes, operating system needs to be aware. But I would argue that there are a lot of good reasons for the operating system to be aware of banks, for example, and subarrays going into the future, so that you can optimize. Since memory is a big bottleneck, I think it makes sense to make operating systems and potentially applications also to be aware of what is the topology of DRAM, so that you can schedule applications better. You can map the data better to different subarrays, different banks, such that applications do not interfere with each other, for example. We may cover memory channel partitioning later on. That's another idea that proposes partitioning the channels between different applications so that they don't interfere with each other. You can take it to the next level of granularity, partitioning the applications across different subarrays so that they don't interfere with each other within a subarray, etc. So I think the best answer is, from my perspective, this work makes a case for making the systems and programmers aware of subarrays. And I think there are other works that also make a case for that. And hopefully the benefits outweigh the costs of that. Clearly, it comes at a cost, right? You need to maintain data structures, no question about that. Today, we maintain data structures about which memory channels. I think going forward, if you really want to solve problems in the memory, we really need to bite the bullet. Does that make sense?
That definitely makes sense. I maybe have a follow-up question regarding, you said that operating systems need to be more intelligent. But for example, if an operating system has more information about the hardware, doesn't that kind of make the chances of like if the operating system knows more, programmers know more, but potentially also malicious people know more, right?
Yeah.
So I'm not sure, I haven't thought this through, but isn't it possible that a RowClone maybe exposes some information about where maybe critical information is hiding? And then knowing where critical information is, you could try to, I don't know, force RowHammer on the row because now you know where it is, right?
maybe, yeah. I don't know actually. I mean, I think that's a complicated question, right? And I don't think I have a good answer to that because that needs to be examined. But certainly, if you have more information about the DRAM system, and if you don't protect it well in the operating system or in hardware, someone may have access to it and they may launch better RowHammer attacks, right? But I will also, I mean, to play the devil's advocate against that argument, I will also say that people already are quite smart enough to reverse engineer the structure of DRAM. Today, all of the RowHammer works have shown us that. Why not just expose this information in a good way so that system can take advantage of it, right? I think basically my argument against that line of thinking would be attackers are already good enough. Basically, they can figure out what is placed where. You're not really making life easier too much for them if you're exposing this information. You just need to protect this information, and you have to solve other problems where you leak information anyway, regardless of this, right? Because the attackers are good enough.
Yeah, I think that's a good answer. Thank you.
Okay, sure. Okay, so there's one question on Zoom. Is there a point in using this technology when copying smaller chunks of data, i.e. smaller than an entire row? If so, can we limit the copy to the relevant bytes? Okay, so remember, there's a interbank copy is actually enabling smaller chunks. You can copy data at the byte, well, not byte, 8-byte granularity, 64-bit granularity, and let's say cache block granularity due to the mapping issues in DRAM. Basically, you can move data in the cache block granularity, which is actually quite good. So it has the capability to do that, and it gives you benefits. Even though this paper doesn't evaluate those, the benefits are there. Interbank copy is not as bad as intersurvey copy, for example. And later works have improved both interbank copy as well as intersurvey copy. So my answer would be yes to that question. There are benefits to it, and people will take advantage of it if that type of support becomes enabled into the future. But if what you're asking is, can you do fast parallel mode inside a subarray and do it selectively on some bytes? I think you should take a look at our SIMDRAM work, for example. The SIMDRAM work enables that sort of support. But of course, if you operate at a smaller granularity, if you want to modify only a small number of bytes, but you really are copying at the row granularity inside the DRAM, the efficiency is not as high as it could be. Okay, these are good questions. Feel free to ask more. Okay, there's some general issues. I think we've been covering some of them: data mapping and interleaving, the granularity. I should add the granularity over here. Data coherence between cache and DRAM, data reuse. All of these are issues with processing in memory, and the paper tackles them. Even though it doesn't propose a lot of solutions to them, it acknowledges them, and it proposes some simple solutions to alleviate the problems. Okay, so if you're interested in processing in memory, clearly we have mentioned that we have this review paper in processing in memory that covers a lot of issues in processing in memory, and RowClone is a baby step, let's say, towards general processing in memory. It's one example of processing using memory, right? As we have discussed, it's not processing near memory, it's processing using memory. Okay, more on RowClone. This is the paper, basically. Now, if there are no questions, then I will cover some history, and hopefully, basically, this is the educational part, if you will, give you some insights as to what happened to RowClone over time and over the review process as well. Yes, there's a question over there. Please go ahead.
So if, like, the US doing the lookup to which method we can use is like some overhead, could we do like something in hardware to make it faster?
What do you mean, which method to use?
Like which of the copying methods?
Oh, okay.
If we can use the fast one, can we implement that in hardware to reduce the overhead?
Yeah, absolutely. And the RowClone paper actually proposes that. The RowClone paper says, okay, you get a mem copy operation from the application, and you have some logic in the memory controller to decide what mode of RowClone to use.
So the information in the US is only needed for like laying out new pages correctly,
exactly.
So that it,
so that you basically so that it gets faster. Yes. So there's no correctness issue, right? Meaning if the application says mem copy and if the hardware supports all forms of RowClone, as long as they're within the same chip, I should mention that, then the memory controller decides which sort of RowClone to use given the data. And after that point, it's a matter of performance. But operating system can, of course, or the application, if it has control, can make it faster by enabling the hardware to use the fast mode more often.
Okay, thanks. Another question. If we have the data already in cache, do we really need to zero or copy the data in memory still?
Yeah, so that's a good question. I think, it depends on how you implement it. But if you're, if you're using the fast mode of RowClone, you have no choice, right? You're copying the 8 kilobytes anyway, right? I think
if we have that page cached, why would we even need to do it in memory if we have like a write-back cache?
Yeah, but the problem is you don't know. You may not. So okay, a page is 4 kilobytes, right? Usually caching happens at 64-byte granularity, and all of these. So 64-byte divided by 4 kilobytes 4 kilobyte divided by 64 bytes is 128, right? No, it's 64. I think it's 64. Okay. You have basically 64 cache blocks. They could be anywhere in your cache. Basically, you don't know which parts of your page are actually cached or not cached. And figuring that out takes time, many cache accesses. So you may not know, first of all, and you don't want to take time. And if RowClone is fast enough anyways, right? If you're copying the entire 4 kilobytes. Does that make sense?
Yeah, thanks.
Okay, sure. You're welcome. But I think you're getting to a trade-off. If you have other forms of copy, like smaller granularities, then of course, where do you do the copy? And I think that's a valid question, basically. If RowClone is doing the copy in 64-byte granularity, or maybe let's say you want to copy 5 different cache lines. Do you want to do it in the memory, or do you want to do it in the cache, or do you want to do it in both, right? And that is an open question. I think there's still some work to be done in that area. That also goes into the general scheduling problem. Where should you do an operation? Should you do it in the L1 cache, L2 cache, L3 cache, or main memory, right? But that's something RowClone doesn't tackle, except for this RowClone Z or insert that we discussed earlier. Okay, very good questions, and I like this discussion. So please, let's make all of the sessions like this. In the past, we had very good discussions in the seminar, and I would like to make all of the sessions like this with a lot of discussion. Okay, now let me give you something that you may not find anywhere else, because I'm going to give you a history of the RowClone paper, let's say, and how it was received initially and what it enabled. And also, I'm going to give you a history of some of the other papers as well. Hopefully, this will be interesting, and hopefully, this will be educational, because this happens in any research that you may delve into the future. Okay, so let me give you the overall historical perspective. Basically, this work is likely the first example of minimally changing DRAM chips to perform data movement and computation. If you find some of their work, please let me know. But we were surprised that we were the first to do it. So it was very surprising to us that it was done as late as 2013. In fact, when we were discussing the ideas with my PhD student, Vivek, I said, let's check the literature. This is such a simple idea. Someone must have talked about it or have done it. And it's not, we couldn't find anything, basically, after all that literature search. There are very high-level nebulous ideas saying, oh, we do copy inside DRAM, but there's no concrete mechanism to provide it. And it led to a body of work on in DRAM and in non-volatile memory computation with hopefully small changes. Later works, of course, became larger and larger changes, but initially the idea was to have small changes. And work building on RowClone still continues. Interestingly, it was initially dismissed by some reviewers. It was rejected from ISCA 2013 conference. And I'm going to give you some insights into what they said, and maybe you can decide how fair or unfair some of these comments are. I will argue that some of them are unfair, as you will see, and it's good to take lessons from this to see how not to review papers. Let's say, basically, some reviewers will get stuck in rat holes, as you will see. I mean, it's not as bad in the RowClone paper, and as it is as bad in the RowClone paper as it is in the Ambit paper, as I will also hopefully discuss. But let's take a look at some early review. So basically, you can see that the proposed. So this paper, this is a reviewer who rejected the paper. He or she or they, let's say they find strengths in the paper, as you can see. They say this is a well-written paper. The proposed technique is simple and elegant. Interesting, very interesting choice of words. Elegant is something that's good, right? It nicely exploits key circuit level characteristics of DRAM designs and minimizes the change necessary to commodity DRAM chips. And the weaknesses, I'm concerned on the applicability of the technique and found the evaluation to be uncompelling in terms of motivating the work as well as quantifying the potential benefits. Details on how to efficiently manage the coherence between the cache hierarchy and DRAM to enable the proposed technique are glossed over, but in my opinion are critical to the narrative. So this was actually discussed in the paper, the DMA approach that we discussed that you can find in the paper. This is an evaluation issue. I mean, you can always ask for more evaluation, but this is the rat holes that I was talking about, basically. As a reviewer, you can always want more, let's say. And rejecting, if you think about works, there's a conceptual component of the work, there's a mechanism component, and there's an evaluation component. If the conceptual component is elegant, and the mechanism is elegant, and if no one has done it, then maybe the evaluation, you need to cut some slack, I will say, to enable scientific progress. because you can always keep rejecting works because of evaluation, as we've also seen in the Ambit paper. And I would like to mention this to you because people are watching us everywhere, I think. And it's important to have an open mind and understand where evaluation fits in terms of the overall impact of a work. If you find it conceptually and mechanism-wise elegant, evaluation may not be as important, right? And that should not be a reason to reject a paper, I will argue, for the sake of scientific progress, because clearly there is some value in the paper. And how bad can the evaluation be, right? You can see the evaluation in the paper is actually not bad, but clearly we can do more, right? I mean, you can always raise the bar to say, why don't you implement on a real system? I'm not going to accept this paper until you implement on a real system. I think that would be terrible for scientific progress, right? Because the real system implementation came after, even not the real system implementation, the off-the-shelf DRAM chip demonstration came 6 years after we published this paper. If it was so easy, someone should have done it earlier, right? After we published the paper. Okay, so hopefully that gives you an example of how to cut some slack for scientific progress purposes, because as a reviewer who's accepting or rejecting work, your role is not just evaluating the every single nitty-gritty part of the evaluation, but also evaluating what would the impact of this work be in the scientific progress. Okay, another review, look at this is actually interesting. Basically, this was rejected by some reviewer B, saying that the idea is not new. And basically, they did not say anything. They said the idea is not new. This is actually an even more unfair review, I will say. If you say something is not new and you don't provide exact reference that does exactly the same thing, then you're being completely unfair. And this reviewer is clearly being unfair. The paper was rejected regardless. Normally, when you get reviews, you normally write rebuttals. This is our example rebuttal, basically saying, reviewer B mentions that our idea is not new. An explicit reference by the reviewer would be helpful here. I would say it's necessary here. We were nice, I think, to the reviewer. While the reviewer may be referring to one of the patents that we cite, we should have said we already cite in our paper. Basically, we cited a lot of patents because we did our due diligence as much as possible, as much as known to us, let's say. And we found a lot of patents that are nebulously talking about moving data inside DRAM, but never proposing a real mechanism like we do in this paper. Basically, we say it to the reviewer. We already cite them in the paper. These patents are at a superficial level and do not provide a concrete mechanism. In contrast, we propose 3 concrete mechanisms, and you can keep reading more clearly. But that didn't work. Basically, that rebuttal didn't work, and these folks rejected the paper from ISCA, as you can see. Well, whatever. I've seen many things in my career. This is not the worst reviews, but clearly this is an unfair review, as you can see. And I will argue that these reviewers are not really thinking clearly. Okay. Now let's fast forward a little bit. This is the ISCA 2015 paper by Google that I mentioned. This was published after our paper was published, and clearly shows that data movement is a big problem in their workloads. And basically, you can see over here, I would recommend, maybe this paper is going to be one of the papers that we assigned as part of the papers you can choose from. And I recommend choosing it if you're interested in this. But basically, these folks analyze all of the workloads in Google's data center, and they basically show where the cycles get spent. And they attribute some of the cycles to what they call the data center tax. This is basically the tax of data movement, for example, compression, allocation, protocol buffers, hashing, RPC, remote procedure calls, and memmove is significant, as you can see over here. So basically, data center tax are prime components for hardware acceleration future data center SoCs. They basically say, we also track all calls to the memcopy and memmove library functions to estimate the amount of time spent on explicit data movement. Explicit, not implicit, meaning exposed to a simple API. This is a conservative estimate. They explicitly say this because it does not track inline or explicit copies. So actually, copies are more costly, basically. That's what they're saying. But just the variance of these 2 library functions represent 4 to 5% of data center cycles. This is exactly the problem RowClone tackles. And this paper was published after RowClone was, luckily, let's say, published. And they basically reference the RowClone paper saying recent work in performing data movement in DRAM, citing RowClone, could optimize away this piece of the tax, which is the memmove and memcopy. So that's what I mean by not derailing scientific progress. If these reviewers had their way every single time in every conference submission, these Google folks wouldn't have been aware of the work that we have done, clearly, because it wouldn't have been published. And as a result, they wouldn't actually say, oh, okay, we find that this is a problem, and there's already an approach that is in literature that should be looked at, right? So this is how reviewers can significantly delay progress if they don't have the right mindset in reviewing papers. But we were lucky, let's say. I mean, we also improved the writing in the paper and some evaluation, but fundamentally, nothing has changed in the paper, I will say. Fundamental idea is the same, mechanism is the same, evaluation may have improved, writing may have improved, and the paper got accepted into Micro 2013, and that's the paper that I presented. So that's good. That's a lucky case, let's say. It was rejected only once. Now, let me tell you about a less lucky case. Again, a work done by Vivek that was rejected 4 times before it was accepted. So Ambit, I mentioned this briefly. This is the first work on performing bulk bitwise operations in DRAM by exploiting analog computation capability of bit lines. It's essentially, it extends and completes our earlier short paper that proposed and OR, but it didn't have NOT. I think having NOT is very important for functional completeness, because now with having NOT, you can have complete algorithms mapped into DRAM. So it's, in my opinion, it's disruptive because it spans algorithms to circuits and devices, and the paper actually covers the entire stack. It requires hardware-software cooperation for adoption. It led to a large amount of work in similar approaches in DRAM and NVM. And the work continues to build, including the compute DRAM work that I mentioned, builds on Ambit work as well as RowClone work. Initially, it was dismissed by many reviewers, perhaps because it was too disruptive. It was too big of an idea to really accept. But I will also argue that the reviewers are also focusing on the wrong things, let's say, as you will see also, hopefully. It was rejected from 4 conferences before it was accepted to Micro 2017. So let me give you the idea so that you can appreciate it a little bit. Basically, you may have seen it, but it basically supports in DRAM and or not a majority. At low cost, but it exploits the analog computation capability in DRAM. And the key idea is activating multiple rows performs computation. And it leads to significant performance energy improvements. And the key idea is applicable to emerging memory technologies as well. I'm going to show you some paper that actually showed that. So basically, the idea is this. Remember the bit lines? Now we have 3. Remember the bit line as well as the rows. Now we have 3 of these bit lines. And imagine each row is 8 kilobytes, and you have many of these subarrays. Imagine basically doing this operation that I'm going to show you across 8 million bits in a subarray, in a single DRAM chip. And the idea is to activate 3 rows concurrently. Remember, this is pre-charged right now, one half VDD. If you activate 3 rows concurrently at the same time, this is called triple row activation. You connect all of these cells at the same time to 1/2 VDD. And with in ideal circuits, you would get charge sharing. And charge sharing would operate such that if at least 2 of these cells are charged, you get the charge state at the end. If at least 2 of these cells are discharged, you get the discharge state at the end. So in this case, at least 2 of those cells are charged. So you get VDD at the end, and you restore all of the charge, and everybody becomes VDD. So the result is really a majority function. The final state of all of these 3 cells is a bitwise majority of the initial state of all of these 3 cells. It's beautiful, right? Bitwise majority function is beautiful, actually. If you read Donald Knuth's The Art of Computer Programming, which I would recommend to everyone, I think volume 4 talks about bitwise majority and its benefits. And one of the benefits of bitwise majority is you can directly implement functions on it, or you can actually take out C, set C to 1, and you get the OR of A and B. Set C to 0, you get the AND of A and B. Now it's beautiful. You can do computation, bitwise computation in a massively parallel manner in a DRAM chip. Okay, you can expose this to the ISA. The paper talks about it. Basically, it takes advantage of RowClone also, but basically it has an implementation. You have a reserved 0, reserved 1 row so that you can do AND or OR, and you have designated rows for triple row activation so that you can reduce the cost as much as possible. Now, if you want to do this, you RowClone A and B into the D1 and D2 to these designated rows in a special DRAM part of the special DRAM subarray, and do the triple row activation, and then RowClone the result into a destination row that's not part of ABC, because result is actually stored in A, B, and basically D1, D2, and D3 at the same time after you do this operation. Yes, there's a question. Please go ahead.
On the previous slide, could you maybe explain what the connection to the inverters are? This N and this.
Yeah, it's the same thing basically. There's the inverter. This is the upper part of the bit line. This is the other side of the sense amplifier. I didn't talk about NOT at this point. So this is exactly the same picture we had in RowClone. This is the enable sense amplifier enabling, which we didn't
okay.
show perhaps. Yeah.
Okay, thank you.
Yeah. Normally there's an enable signal to the sense amplifier that's controlled by the DRAM chip. We're just showing it over here. So you need to enable the sense amplifier, but the DRAM chips enable the sense amplifier internally when you do the activation. Make sense? Okay.
So another question. So why do we need these special ABC rows for doing the computations, or D0, D1, and D2?
Yeah. So
I mean, it's not. Why is it expensive? We have like the same activation mechanism like we already had, right?
Yes, but it's triple row activation. Basically, to be able to do this, you need 3 row decoders, right? And row decoders are very expensive in DRAM. So if you want to do it on arbitrary rows, any possible row in DRAM subarray, you can do it, yes. But you need to be able to have 3 row decoders. And row decoders are really expensive in DRAM because they're logic. They're not optimized for the DRAM process. That's the main reason. Hardware cost is very high, basically.
So the decoders, what are they doing? They are activating the rows or what?
Well, they're selecting the address of which row to activate. So you may have, for example, 1,000 rows in DRAM subarray. You need to have a 10-bit address and decode it and select the word line, right?
Yes, just a couple of AND gates, right? And with not.
Well, it's if your address is 10 bits, it's really AND tree. Let's say it's a tree of AND gates.
Okay, yeah, makes sense.
Yeah,
Thanks.
and those AND gates need to be large, and those AND gates are implemented in the DRAM process, which is not friendly to logic process. As a result, they occupy a lot of area in DRAM. So you want to minimize the row decoders.
Yeah, okay. So we just have one special address which activates 3 special rows.
Exactly. Here, row decoding is minimized, actually. If you have, well, I didn't talk about the paper in detail, but you get the idea, basically. You can actually have very minimal decoding if you do what we suggest over here.
Yeah, makes sense. Thanks.
Okay. I mean, I don't want to cover the entire Ambit paper. It's good that people are asking questions, but all of these answers actually are also in the Ambit paper. If you're interested, you can read it. I'm not going to go into detail, but this was fast bulk bitwise and OR. So you can also do NOTs. NOTs is a little bit more disruptive, let's say. So if you actually activate a row, the complement of the cell is actually on the other side of the sense amplifier. So basically, you activate one cell. The bit line stores the value of the cell. The other side of the sense amplifier, cross-coupled inverter, has bit line bar, meaning the value complemented. So you already have the inverted value somewhere, except in existing DRAM, you cannot connect it back to the same subarray. And that's what Ambit paper does. It proposes some small modification to the DRAM chip, such that you can feed the already negated value in the sense amplifier into a special row. So basically, complement computation is already done in DRAM through activation. We just feed it to a special row. That's the idea. This way you can do NOTs, but of course, this comes at a cost. Again, I'm not going to go into details. You need to read the paper. This works. There's SPICE simulation in the paper that shows how it works exactly. There's reliability simulations, etc. And this is the cheapest way of implementing NOTs in DRAM without actually adding any logic to DRAM other than interconnect and some logic to move data into a special row. So this is overhead, of course. Okay, so the paper shows that the performance is significant for NDRAM bitwise operations. I'm not going to spend time on this one, but there's a lot of comparisons in the paper also. And you can see that energy is significant. Energy gets reduced by 60x almost for NOT, and you can build XOR, XNOR operations, etc. on top of the AND or NOT primitives and majority and NOT primitives also. And this is the bulk bitwise operation performance. NOT is the fastest and highest energy efficient. But of course, if you take a mean average across all of these operations, it's still quite significant, as you can see. And the Ambit paper then says basically bulk bitwise operations are actually employed in many different applications. And Ambit paper evaluates them in simulation. For example, bitmap indices, bitweaving databases that are especially designed to maximize bitwise operations so that they can execute on GPUs, and then bitfunnel, web search engines, DNA sequence mapping, etc. The paper evaluates set operations, bitmap indices, and bitweaving, for example. I'll give you some examples. So for example, you may have a lot of bitmaps in your database that store the data in a categorized manner. So if you're searching for people who are within some age range, you take that bitmap. And you're also searching for people who are attending ETH. You have a bitmap for people attending ETH. and if you want to combine predicates, let's say people who are within this age group, who are attending ETH, who live in Zurich, who, I don't know, were born, I don't know, in Sweden, and who have traveled to 50 other countries. You have bitmaps for each, and this is a good way of representing data in a database. And the predicate computation is essentially bulk bitwise computation in the entire bitmap. So you have a lot of bit level parallelism and a lot of bitmaps. And this is a very good fit for Ambit, for example. And Microsoft has designed a web search engine to operate in a similar manner, like these bitmaps. And the Ambit paper shows that you can actually improve the bitmap performance, bitmap query performance significantly. This is end-to-end in simulation, of course, because clearly it's very difficult to manufacture this chip. And it also shows that if a database is designed for specifically maximizing bitwise operations, and we were lucky to have a database like this. Some folks designed the bitweaving database because they were forward-looking. They wanted the database to do nice column scans on GPUs, which are good at bit-level parallelism. We basically ported that database, Vivek ported that database into our simulation infrastructure and showed that you can get significant benefits with Ambit. In simulation, of course, as you can see. So this sounds all very good, right? Hopefully. And these are the papers that have introduced Ambit. And later work actually built on Ambit to make it even more general. So this is more recent work from our group that makes Ambit more general. And if you really want to learn more about Ambit and computation in memory, we cover it in the advanced computer architecture class and talk about Ambit in more detail. Okay, I've already said this, but now let's take a look at the reason I'm telling you all of this is, again, talking about the mindset, right? So that I can help you set your mindset in a good perspective so that you have the right trade-offs in mind when reviewing papers. And this is extremely important, in my opinion, for scientific progress and accelerating scientific progress. I believe Ambit paper had a lot of impact in later works. Again, you don't need to trust me. You can look at the record of the paper. You can talk to people who have read the paper also in industry. But this was rejected from 4 conferences. Now, there's a mindset issue. That's why I'm going to talk about it. Basically, many other papers are rejected in similar ways for, let's say, trivial reasons. When the papers are rejected for good reasons, that's okay. But when the papers are rejected for trivial reasons, that's a bad thing. That's really delays scientific progress. And we're not even talking about industry standards, industry interfaces yet, right? Because industry tends to be conservative. But in research, we should really leap forward and find good ideas. So the question is, how do we fix the mindset problem? Clearly, we need to do more research, education, and implementation, alternative processing paradigms, and how to review papers, let's say. So we really need to work on enabling the better future. The goal is not to really cave in and only work on ideas that are easy to evaluate, easy to satisfy your viewers with. That's a bad approach. That's terrible, actually. The goal is really to do the right thing and do strong research, look forward, look into alternative processing paradigms, but also educate people who are doing the reviews. So let me give you an example of what happened to Ambit. This was ISCA 2016. That was the first conference it was submitted to. It was rejected. It was called BuddyRAM at the time. In fact, we actually released an archive version of Ambit. It was called BuddyRAM also. You can see that there are rejects. Micro 2016, it was also rejected. I don't remember what it was called at that time. It doesn't have this information over here. HPCA 2017, it was also rejected. In fact, some reviewers was strong reject, as you can see. We'll see some reasoning. ISCA 17, it was also rejected. You can see the reviewers became somewhat divided, as you can see, but it was rejected in the end. It was accepted to Micro. Of course, it sounds good, no? But let's see the reviewer's thinking. So this reviewer is a reviewer who rejected the paper. Very clever, novel idea. Great potential speed up and efficiency gains. You would expect this should be an accept, right? But look at the reason why it was rejected. Probably won't ever be built. Not practical to assume DRAM manufacturers will change DRAM in this way. I would say this is an extremely unfair review. This is terrible because this is speculative, right? You cannot evaluate an idea in terms of what will happen to it in the future because who knows the future, right? I don't know the future. You don't know the future. I don't know if there's anyone among us who will know the future anytime soon. Yet this review is purely based on speculation, and the reject is purely based on speculation. And not even good speculation. It even says probably won't ever be built. And this is a reject. So I will argue that never do this. You cannot reject a paper based on pure speculation. Okay. Okay, another review from the same conference. I found this idea very interesting and novel. In particular, blah, 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 blah. So these are good points basically about the paper. The benefits are good, a huge degree of data parallelism, very interesting and novel, but the biggest problem, again, the similar mindset. It underestimates the difficulty in modifying DRAM process for benefit in only a subset of applications which do bulk bitwise operations. In particular, I find it hard to believe that the commodity DRAM industry will incorporate this into their standard DRAM process, blah, 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 blah. You can read forward, basically. Basically, it's saying essentially the same thing, maybe in milder terms, saying it will never be built, right? Again, this is a speculative thing. You cannot evaluate a paper based on the future. You can say, okay, yes, I have these concerns, but nobody can do anything about these concerns at this point, right? I mean, even the paper cannot do anything about it. Even if the paper actually showed a DRAM prototype with this, you can always argue that, okay, it's not a DRAM prototype built in the finest DRAM technology of its time, right? Clearly, we cannot build a DRAM prototype that's going to be at the cutting edge. And the issues always arise with the cutting edge. And building a DRAM prototype for this is actually a lot of challenge. It's not like building a processor prototype, which is very easy today. DRAM is very difficult to build, actually. Okay, another review. This requires a modification to DRAM that will only help this type of bitwise operation. Again, it seems unlikely that something like this that will be adopted. They're not evaluating the idea, they're evaluating speculation. You never know, basically, what will be adopted. Again, machine learning was not adopted until GPUs showed that it's feasible, right? So basically, reviewers need to have some good insight and should not really reject papers because of these speculative reasons. Again, another review. I can show you all these reviews that say this will not get implemented. Basically, it's another review. Basically, this is another review that's interesting. That's a bit different in its reasoning. I do not find architectural innovation, even though the circuits technique benefits architecturally by mitigating memory bandwidth and relieving cache resources. The only related part is the new ISA support for bitwise operations and cache coherence issues, etc. And the paper says, oh, I'm an architect. Why are you bothering me with this? I think it's wrong. Basically, the paper, they say you should fabricate the chip and publish in a circuit conference. I do not know of many groups that fabricate DRAM chips and publish them in circuit conferences. In fact, only the top DRAM manufacturing companies do that. They do it only once in a while, and they do not reveal any information as to their techniques. They only give high-level information. They say, oh, we implemented ECC. And this is the chip. Good luck with it. Basically, I think this reviewer is basically, first of all, is unfair in the sense that it's ignoring all of the architectural benefits and workload benefits of the idea. And it's basically raising the bar so high that no one can do it. No one other than DRAM manufacturers whose business is this, and they don't reveal information, basically. Okay, let's move to HPCA 2017. These unfair reviews never end, so it's good to, I think, look into these. Again, the purpose is not to be these reviewers, to understand what's wrong with these reviews and not to be them. So, okay, you can see that strength seems like a new idea. Processor and memory ideas have researched. This is a very sloppy review, I would say, basically. This reviewer doesn't want to really acknowledge something about the paper. It seems almost like he has some hidden agenda in rejecting the paper. Okay. Who knows what else that agenda is, right? Maybe they're promoting some other type of processing in memory. Maybe this is a review from industry. Who knows? We don't know. But look at the reasons for rejection. Impractical, too many implications on ISA, DRAM design, and coherence protocols. So you could reject any processing in memory paper that way. Unlikely to benefit real-world computations. How do you know that? The paper does evaluation and shows that there's significant benefit in real-world computations, right? So basically, this paper ignores evidence provided in the paper, and this reviewer ignores evidence provided in the paper and provides a, let's say, completely subjective evaluation saying unlikely to benefit real-world computations. How do you know? Evaluation did not consider full program performance, which is also incorrect, actually. The evaluation does consider full program performance. Okay, so it's very interesting to read these reviews, basically. I'm skeptical that this will benefit real-world computations. I've never seen so this is very interesting because I've never seen real-world program profiles with hot functions or instructions that are bitwise operations. The paper actually provides evidence toward that direction by showing applications. I've already given you bitmap indices, right? This is a very unfair reviewer. You should never do this, basically. You cannot say, oh, I've never seen it. Who are you, right? You may be the expert, but that's fine. You should still step back and say, these and these papers show that bitwise operations are not common if you're going to actually reject the paper for that reason. You cannot reject it by saying, I've never seen this, right? Very bad, let's say. On the other hand, which is interesting, and I think with the RowClone discussion we had, you will find this very interesting. On the other hand, I have seen system profiles that show non-trivial time zeroing pages. I suggest you retool your work to support page zeroing and evaluating, blah, blah. Take a look at when and why Linux kernel zeros pages. You might be surprised at the possible impact. I think this reviewer should probably be aware of the RowClone work, which was published 4 years before Ambit was submitted for publication, right? And I think you are witnesses of that also, right? Clearly, zeroing pages is done by RowClone work. Why rehash old ideas, right? So this review is perhaps one of the utmost unfair reviews that I have seen. Well, maybe in my life is a big claim because I've seen many, many unfair reviews. And that's why I think there's a huge problem in scientific progress. But this is an example of what I'm talking about when I talk about unfair reviews. Basically, don't ever be this kind of person. I don't know how this reviewer can write this and sleep well at night, but I guess, yeah, unfairness is built into some people. Okay, another review. This is also interesting. It's also a reject, as you can see, weak reject. The previous one was actually complete reject, as you can see. I don't want to even consider it, basically. They didn't consider the rebuttal. This one is a weak reject, but still a reject. Conceptually very interesting, considers various aspects of interaction, blah, blah. Negative impact on, essentially, again, impact on DRAM design. So you will see this more and more in DRAM ideas, processing in memory ideas. But you know that that's also happening, despite the reviewers. So this reviewer claims that they understand the difficulty of DRAM overhead analysis, but that they get stuck on it, basically. So this is a reviewer that may potentially understand that evaluation is not as important, but they still get stuck on it. Don't get stuck on evaluation issues. Evaluation can never be perfect, right? And papers have value beyond evaluation, clearly. Okay, this reviewer is also another one, as you can see, not motivated, well, not convinced, blah, blah. Not good English also, as you can see. Yeah, anyway, I'm not going to belabor this. You can read these reviews on your own, if you will. But basically, this reviewer also targets things that the paper clearly acknowledges that it's not going to solve. What happens if the user does a bitwise operation on 2 8-byte data and wants to store it in a third block? Again, that's not what we're trying to solve. You really need to rewrite your application such that it operates on large granularity data, and later works actually showed that you can actually do it. Okay, I think you can actually pick on more and more of these reviews over here. Yeah, I think we're already out of time. I actually have fun looking at these, but I don't want to take more time. But basically, the paper was rejected from the last conference it was rejected from. And I will let you, I guess, read the PC program committee summary. This paper was discussed online at the PC meeting. The reviews were uniformly positive about the novelty. So novelty is good. However, the reviewers were also concerned about the feasibility, which will never be evaluated perfectly in a single paper, basically. They don't say this, of course. But you can see these are all things that are evaluated in the paper. Impact of process variation on the design's functional correctness, that's evaluated in the paper. The potential reliability issues that arise due to lack of blah, blah. The impact on DRAM testing cost, which no one can easily evaluate other than the DRAM manufacturers, and they will not tell you even after they evaluate it, because this is their trade secret. Okay, you can see how trivial the comments have become, right? You have this big idea that people consider, okay, this is a big idea that can actually have a lot of, it has a lot of novelty. That's also acknowledged here. It boils down to simulations that are performed to address variability. Monte Carlo cannot capture tail distribution of cell failures. Also, Monte Carlo cannot capture random correlated failures, etc. And given these huge concerns, the program committee ultimately decided to reject the paper. And nothing has changed in the paper later. We acknowledge all of those reviewers. Well, nothing substantial, let's say. Nothing substantial has changed in the paper, except it went to a better set of reviewers, let's say, who are, let's say, more open-minded about ideas in general and conceptual contributions and mechanism contributions. And they don't get stuck on the nitty-gritty of how many Monte Carlo simulations did you perform in this paper. And the paper was accepted to Micro 2017, but I would have said that it could have easily been accepted to any prior conference because nothing fundamental has changed in the paper, I will say. Of course, writing improved, etc., but fundamentally nothing has changed. So this is why I recommend that book that we recommended in earlier discussions, right? The Art of Computer Systems Performance Analysis. This beautiful book by Raj Jain says that even if everything is done correctly, specifically for performance analysis, and presented, it may not be enough to persuade your audience. decision makers. In this case, decision makers are accepting or rejecting the paper to follow your recommendations. The list shown below in this box is a compilation. Well, in the next page, actually, this is a pictorial representation of that box distilled of reasons for rejection heard at various performance analysis presentations. You can use the list by presenting it immediately and pointing out that the reason for rejection is not new and the analysis deserves more consideration. Also, the list is helpful in getting the competing proposal rejected. He is making a joke, of course, over here. So basically saying there's no clear end of an analysis. An analysis can be rejected simply on the grounds that the problem requires more analysis. And that's the first reason listed in box 2 over here. This needs more analysis, right? And that's what these reviewers are doing. This needs more analysis, come back. This needs more analysis, come back. This needs more analysis, come back. But the cost of that is significant, basically, in terms of scientific progress. The second most common reason for rejection is workload. And that's what the reviewers are also doing, right? Oh, the workloads. I don't believe the workloads. I don't believe the workloads. And they're doing it in a very bad way, in a very subjective way, right? Since workloads are always based on past measurements, they're applicable to current or future environments can always be questioned. Actually, workload is one of the 4 areas of discussion that lead a performance presentation into an endless debate. These rat holes and their relative size in terms of time consumed are shown in this figure. And presenting this cartoon at the beginning of a presentation helps to avoid these areas. So maybe we should present this cartoon in all of the papers that are written. But that's not an efficient way of using the paper space, clearly. So workload, metrics, configuration, experiments, detail, as you can see. Okay, so I like this pages a lot, and I would recommend you to read them also. But I like one of the reasons for not accepting the results of an analysis. Why change? It's working okay. And the reviewers are also doing this. If you think about the comment, DRAM manufacturers will never implement this. Essentially, that's what they're endorsing. They're changing. DRAM manufacturers are doing the right thing. Who are you? I don't want to publish this paper because why change? DRAM manufacturers are doing the right thing, right? That's essentially the mindset that rejects the papers. And don't ever be that reviewer because you are a cliche, let's say, in this book, in that sense. Okay, that's why I present actually these suggestions to you. Be fair. Even if you're the expert, you do not know it all. Be open-minded. Even if you're the expert, you do not know it all. Be accepting of diverse research method. There's no single way of doing research. There's no single way of doing evaluation. There's no single way of writing papers. There's no single way of exporting ideas. Be constructive, not destructive. I would argue that a lot of these reviewers are quite destructive. Their goal is not to construct. Their goal is to really maybe, I don't know what it is. Either promote their agendas such that these papers are rejected. Maybe they have some hidden agenda. I don't know, or maybe show their ego by showing how experts they are. We don't know, but certainly they're delaying science. And reviewers should enable heterogeneity, meaning be accepting of different diverse methods, but they should not have double standards. Basically, they should not accept some paper that's for a reason that they reject some other paper, let's say. Or if a paper has the same issues as some other paper, they should not be accepting one and rejecting others, because that raises a lot of questions as to why you're doing this, right? So basically, this is my recommendation, and I actually put this recommendation in many scientific venues also. Reviewers should not be blocking or delaying scientific progress for non-reasons. And I think I've given you many non-reason examples. So we need to fix the reviewer accountability problem. Just like main memory needs intelligent controllers, I think research community needs intelligent and accountable reviewers. Okay, I think there are more examples of my recommendation. In fact, the first place where I talked about these recommendations are actually in the speech that I delivered at the ISCA conference, but I've been using this afterwards also. Now, let me give you the idea of compute DRAM. So these reviewers reject the papers. They're saying it's not feasible. DRAM manufacturers will never do it. You didn't implement it, etc. After our works were published in 2013, RowClone, and 2017, Ambit, basically this compute DRAM work was published in 2019. And they basically show that off-the-shelf DRAM chips are capable of doing these operations in a limited manner. And I will argue that this is a success of validity of our ideas. Even though DRAM is not designed to do any of this, these folks actually did a great thing by showing that DRAM can do it, right? To some limited extent. Let me give you the idea very quickly. Maybe some of you will present this paper. I don't want to actually steal that thunder, but basically they show that you could do row copy operations similar to RowClone. You could do logical and OR similar to Ambit. You cannot do NOT because that require modifications to DRAM significantly, as we discussed in the Ambit paper. So they cannot do NOT also. So what they do is not functionally complete. But let me give you the idea. Basically, you can do RowClone by actually doing one activate and then changing the timing in the memory controller such that the second activate happens very, very quickly. So you do the second activate very quickly such that you mimic 2 consecutive activates just like RowClone does. And they show that by doing this in the memory controller using real DRAM chips, you can actually get good results of row copying in real DRAM chips. I'm going to show you that results also. So this basically nullifies a lot of the arguments the reviewers made, as you can see. So bitwise AND is a little bit more tricky. What they do is they do activates and then they do pre-charge. So basically very soon after the activate, they do pre-charging, but that T1 is very short so that the sense amplifiers are not activated yet. And then they do another activate to another row. It turns out if you do this, the row address transitions from 01 to 00 to 10, and all of these 3 word lines get activated concurrently for a brief amount of time. So even though the DRAM chip is not designed to do triple row activation, just because you're doing these activate, pre-charge, activate consecutively by violating the timing standards in quick succession, you're forcing the DRAM chip to do a triple row activate in turn. You can call it by luck, but it's by design also potentially. If anything that can happen by luck can also happen by design, right? So these folks show that you can actually do triple row activation in a limited number of chips. And they actually use our SoftMC infrastructure, which was mentioned in a previous lecture. SoftMC is the FPGA-based infrastructure that we designed to test DRAM chips. And these folks actually build on it. They add some heating infrastructure on top of this. And they basically test these ideas in a modified memory controller using these chips, as you can see, and real chips, off-the-shelf DRAM chips, similar to a lot of the studies that we have done. And they basically provide the proof of concept, and they talk about how they test the modules. I'm not going to talk about the experiments, but these are real experiments on real DRAM chips. And this is the key result, basically, that they show. Basically, these are different chips over here, as you can see. Each grid represents a success ratio of operations for a specific module. I should say these are real modules. And you can see that green means you can do AND and OR on all columns. So there's one module where you can actually do this triple row activation. Clearly, it's not a lot. And there's another module where you can actually do triple row activation. You can argue why this is the case, but we don't know the internal workings of these chips. Just the fact that you can actually do triple row activation in these chips and get AND and OR is significant. RowClone is, of course, easier, right? Because it's not triple row activation, which is very difficult to do in an existing DRAM chip. It's 2 consecutive activates. And they basically show that you can do RowClone, row copy on all columns in many chips, as you can see. And RowClone is successful on a fraction of the columns in many chips also. So you can see that there's a limited amount of success, but there is success, meaning you can actually do it on some DRAM chips and some columns in a very reliable manner also. 100% of the columns are actually capable of doing RowClone, and 100% of the columns are capable of doing AND and OR. So this is, I think, a very nice proof of concept that validates our past ideas, and hopefully maybe provides a lesson to the reviewers that have rejected the works. And I think I'm picking on this work because I know the history really well, but I know that this sort of rejection is happening not just on our works, but on many works that have the potential to leap forward the field to a better state. Okay, I will also recommend you take a look at the Pinatubo paper that was also published later. These basically do, so they basically do, I should say over here, n-row bitwise operations. They basically do it in phase change memory chips, in non-volatile memory chips. They show that they can do RowClone and also back bitwise operations, and they show good results. Okay, I think I've spent a lot of time. Hopefully it was interesting. I have a lot of other examples over here. Mindset issues are everywhere, but I don't have time to cover them. But my advice to you as researchers who may receive this sort of reviews is follow your passion. If your idea is fundamentally good, then do not get derailed by naysayers. So one approach to receiving this sort of reviewers is saying, oh, okay, these reviewers don't accept my idea, so I'm going to forget about it and move on. That's a bad approach. Believe in the idea. Of course, if the idea is big, if the idea is really small, maybe you decide to focus on bigger things, right? But if your idea is big, and we are convinced that all of these ideas are big from our perspective, follow your passion. Do not get derailed by the naysayers. Be resilient to all of this. In fact, our original RowHammer paper was also rejected, even though we showed real system results. So you can never satisfy some reviewers. Let me put it that way, because they don't have the right mindset. Be resilient. Focus on learning and scholarship. Focus on improving the quality of your work, and the quality of your work eventually decides your impact. And hopefully you will get past the reviewers at some point. But working hard to enable your passion is important, as we discussed in one of the earlier lectures. Building infrastructure is important. And I think once you do that, you can make a good impact on the world. And I believe RowClone and Ambit papers, despite all the difficulties that I have described, have made a good impact on the world. And if you're interested in more, I think you can look at these speeches and this interview and this talk that I mentioned before. I will also mention the suggested reading that we didn't mention before. Richard Hamming, in this talk that he delivered in Bell Labs. Probably many of you know Richard Hamming, who invented the Hamming codes, error correcting codes. He delivered this talk on how to be successful in research to the researchers in Bell Labs in 1986. And I think he has very nice insights over there that I will recommend. Basically, he says, if you really want to be a first-class scientist, you need to know yourself, your weaknesses, your strengths, and your bad faults. How can you convert a fault into an asset? How can you convert a situation where you haven't got enough manpower to move into a direction when that's exactly what you need to do? Basically, how can you convert a situation where you get these bad reviews to your advantage? It may look like it's not easy to do, and it's not easy to do, but I think by being resilient, you can do that. So I think this is actually very good advice. I claim that some of the reasons why so many people who have greatness within their grasp don't succeed are they don't work on important problems. They don't become emotionally involved. And I think emotionally involved means that you will need to be resilient in the face of all of this adversity, let's say, against your work, even though, let's say, unfair, even if the adversity is unfair, right, completely. They don't try and change what is difficult to some other situation, which is easily done, but is still important. And they keep giving themselves alibis why they don't. They keep saying that it's a matter of luck. In the end, it's not a matter of luck. You enable actually, the preparedness enables your luck also. Okay, I would recommend this beautiful transcript as well. And Hamming also has actually a series of lectures that he has delivered at the Naval Postgraduate School in the US from 1995 that covers a lot of these. And I will mention that maybe in the future, or you can find that online as well. Okay, I think we're done. We took some more time than I expected, but there were a lot of good questions in the meantime also. But I wanted to convey this perspective also. So it's good that some of you stayed. You didn't have to, but thanks for staying. If there are any questions right now, I'm happy to take them. Feel free to ask them. But I also understand if people want to leave at this point. Any questions? I see no questions in the room. Maybe people are tired, and that makes sense. What about questions in Zoom? Okay, or YouTube, I guess. Any questions? Okay. I guess if there's nothing, then we will see you in the next meeting. And I think by the time of the next meeting, hopefully we will release the papers that we would like you to select and prioritize, hopefully so that you can give presentations like these examples that we have been covering. So be on the lookout and take care. Have a good evening and have a good weekend. Okay, thanks. There's a comment on Zoom saying, thanks for the presentation. That was insightful. I hope so. I hope it was useful for you. Okay, I think this is where I will end the live stream as well as the Zoom meeting. So I will see you all next week.